Have you ever stopped to think about the engine that's running all the AI in our lives? I mean, it feels like magic, right? But it's not. It's math. And today, we're going to pull back the curtain on the one piece of math that makes it all possible: linear algebra.
I mean, really think about it. How does your phone know it's you and not someone else in a split second? Or how does YouTube queue up the exact video you didn't even know you wanted to watch? It's not a mystery.
It turns out, all of this tech speaks a secret language, a language made entirely of math. And the specific dialect AI uses to get all this stuff done is called linear algebra.
Okay, so let's dive into section 1. At the end of the day, every AI system has to solve one big problem first. How do you take our messy, complicated world and turn it into something a computer can actually work with?
See, computers only get one thing: numbers. That's it. But our world? It's full of images and conversations and music and all our different choices. So bridging that gap from our world to the computers is the first, most important job for any AI. And the tool that builds that bridge is something called a vector. Now, don't let the name scare you. A vector is just a list of numbers. That's all. Think of it as AI's universal translator. It can take pretty much anything, a picture of your cat, your taste in movies, and turn it into a list of numbers the computer can understand.
All right, on to section 2. Let's get practical. How does this translation from data into numbers actually happen? Let's look at a few examples.
So take a picture. To you and me, it's a photo. To a computer, it's just a big grid of numbers. Every single number in that grid just represents the color of one tiny dot, one pixel. For a black and white photo, you could have 0 for white, 255 for black, and all the shades of gray in between. Yep, it's really that simple.
But what about something you can't see, like your taste in movies? Well, you can turn that into a vector too. Just imagine a really long list of movies, and for each movie there's a number from, say, 1 to 5. That's your rating. Boom! Dot list of numbers is a vector that represents your personal movie taste.
And words? How do we handle words? Well, one popular way is called one-hot encoding. You basically give every word its own list of numbers. The list is all zeros, except for a single 1 in a unique spot for that word. So as you can see here, the 1 for cat is in a totally different place than the 1 for tiger. It's a simple trick to give every word a unique number ID.
But there's a really big problem with this. Using this method, the computer has no idea that a cat and a tiger are related. To the math, the vector for cat is just as different from tiger as it is from apple. And that's a huge problem if you want an AI that actually understands what things mean.
So how do we get the AI to see the meaning behind the numbers? How does it learn the relationships hidden in the data? Well, that's exactly what we're going to cover in section 3. One of the most important tools for this is called the dot product. It's basically a special way to multiply two vectors together, and when you do, you get a single number that tells you how similar they are. A really cool way to think about it is like the shadow that one vector casts on another. The bigger the shadow, the more similar they are.
Now, let's go back to our word problem. If you take the dot product of the one-hot vectors for cat and tiger, you know what you get? 0. A big fat 0. That number tells the computer they have absolutely nothing in common. So clearly, we need a smarter way to do this.
And that smarter way is something called vector embeddings. Basically, AI uses some clever techniques to take those long, simple vectors and shrink them down into shorter, denser vectors that are packed with meaning. In this new setup, the vectors for cat and tiger would be really close to each other, mathematically. And the vector for apple, it would be way off in another direction. This is the magic behind how recommendation engines work. Okay, section 4. We've got our meaningful vectors now. But real-world data is massive and incredibly complex. How does linear algebra help AI deal with all of that information without getting totally overwhelmed?
You know, real data isn't simple. It often has hundreds, even thousands, of different features or variables. We call this high-dimensional data. Trying to find a pattern in that is like being told to find a specific shape inside a massive, swirling, chaotic cloud of dots. It's almost impossible.
This is where linear algebra comes to the rescue again. It gives us the tools to find a simpler view, like a flat slice, right through that messy cloud of data, a slice that still holds most of the important patterns. We call this dimensionality reduction. It's all about finding the signal inside all that noise. And the special math tools that find these perfect slices are called eigenvectors. It's a fancy word, but you can just think of them as arrows that point out the most important directions or trends in your data. By focusing on just those directions, the AI can ignore all the random noise and see the simple, hidden structure that really matters.
All right, let's bring it all home. In our final section, we're going to connect all these dots and summarize the true, vital role that this math plays in pretty much all modern AI.
So why is this stuff so critical for AI? Well, first, it's the translator. It turns our world into numbers using vectors. Second, it's the judge of relationships using things like the dot product to measure similarity. Third, it creates smart data through embeddings, so the AI understands meaning. And finally, it makes the whole process fast and efficient by cutting through the complexity. This isn't just nice to have, it is literally the foundation of modern machine learning. So, the next time your phone unlocks just by seeing you, or an AI suggests a movie you end up loving, maybe you'll think about it a little differently. Will you be able to see the elegant, powerful math that's working behind all that magic?